So good afternoon, everyone. Our research paper title is Implementation of Master Side of APB Protocol using Verilog Systems. The basic introduction I would suggest is it is part of the AMBA bus protocols. It is used as it is an on-chip system protocol. The main lucrative point of APB is its low-cost interface and non-pipeline architecture. It provides us extreme efficiency with low power consumption and reduces interface complexity. It is also very useful for connecting low bandwidth peripherals, meaning when we put it in a system of including the computer system. For example, in this diagram, as we can see, the AHB or ASB is the advanced high peripheral bus. This bus is connected to the CPU and the ARM processors, as we can see. And while APB is connected to the low cost, low bandwidth peripherals such as UART, timer, keypad, and PIO. It basically acts as a bridge between these two types of protocols. When we were doing the literature survey, we were able to identify various ways and methodologies in which we could implement and verify our design. So most of the surveys included about functional verification and simulating the device under test by providing specific instances to the values. The basic what we have learned from this literature survey is to implement a design that will provide us maximum frequency even at lower consumption of dynamic power. As we can see a block diagram, this APB master will enable P enable signal to the slave, and the P select signal will select which slave is to be chosen from among the slave options. P address, P write, these are various signal descriptions that we've used. The P slave error helps the master to know in case there is an error in the transfer operation, and this will help the master to identify by letting itself know. Now we will progress towards the basic reason why we're explaining that reduced power consumption is also because even though dynamic power is directly proportional to frequency and our design operates on 50 hertz of clock frequency, we were able to identify, as we can see in this diagram of operating stages, our design operates in 3 operating stages: idle, setup, and access. In the idle state, no transfer occurs. This is the default state of our APB. When it moves to setup state, a transfer is required. The bus moves to setup state, where the appropriate signal P select is asserted. The bus only remains in the setup state for 1 clock cycle and always moves to access state in case the transfer is identified. Now, if the P ready is 0, it will stay in the access state until the P ready becomes 1 and the transfer occurs. So the main transfer operation occurs in the setup and access state. And in case this is not occurring, then it will go to idle state in order to save the power. Now, I would request my colleague Hitanshu Vibhute to continue and explain more about what we have implemented.
Okay, so like as my partner said that we have successfully like designed and implemented the APB interface. So this is basically the design summary that has been generated by the Xylene software. So as you can see, like the usage, right? Other than the bonded IOs, because the width of data bus and address bus in this project is 32-bit. That's why the IOB utilization is very high. But otherwise, you can see like the number of resources like LUTs, flip-flops, buffers, and all mux we are using are very less as compared to what is actually present on FPGA. So our device utilization factor and the area optimization is like we can say low. So we were able to like optimize our area by 4% in like 2 to 3 stages of design. So there were also latches which were formed during the design. So we were able to debug and remove the latches. So latches are basically very harmful for the design. So this design does not has even a single latch. Can you go ahead? Yeah. So as you can see, like the maximum achievable frequency, the frequency that we are able to achieve is 598.463 megahertz. So EPB is a low bandwidth interface, so it can support like from anywhere from 5 megahertz to 110 megahertz. But in our case, our design is able to support the frequency of 598.463 6.463 megahertz. So this report has been generated by the Xilinx software. So similarly, as you can see on the right hand side, the power supply summary, the highlighted part. So the dynamic power consumption is very, very low. That means like our design is operating on very low power, that is 54.06 milliwatt. So can you go ahead? Yeah, so this is basically the waveform that has been generated. That shows that we have successfully verified our design and is matching with the specification sheet, the waveforms given in the specification sheet. So like we have tried doing a bunch of write operations in this. So as you can see, like uh, ignoring the initial clock cycle, as I'm applying the reset at 25 nanosecond, our states are continuously changing like per clock cycle. So as you can see, like we have used external registers like address and write data register. So this helps us verify that our design implementation is successful. So as you can see, like the values in P address and address are matching. So as well as the write data and PW data is also matching. So this shows that our design is uh, working perfectly, and as well as for PR data. So PR data is basically like reading from the slave. So can you go ahead? Yeah. So as you can see, like the value which is in read data out is matching to PR data. So this also proves that the read operations are successfully taking place. So yeah, go ahead. So yeah, these are just the advantages. So basically, like when we need an interface, as designs are getting complex, we are having high frequency cores in our SOCs or ASICs. So that's why we need some protocol interface uh, in order to meet the gap between the low bandwidth peripherals and the CPU and the other high frequency buses. So yeah, so these are basically the applications. So it is generally used in almost every device. This is like the part of ARM architecture which is used in our mobile phone, laptops, and microprocessors controllers. And these are the reference papers that we have referred. And most of the reference part is done uh, on the ARM specification datasheet. So we have used the datasheet specification in order to design and implement our design.
Okay, thank you so much for your kind presentation.